James Ellery is a senior engineer at Frazer-Nash Consultancy, having over 10 years' experience in research and development. Frazer-Nash is an engineering consultancy that undertakes a broad range of projects in energy, infrastructure, transportation and defence. The UK government is actively looking at methods of decarbonising heat and has commissioned Frazer-Nash to investigate the engineering challenges of developing domestic gas appliances, boilers, hobs, ovens and fires that can operate on 100% hydrogen. So that fits very neatly into what we've just heard from Vikram. Welcome, James. And topic, domestic hydrogen appliances for decarbonising heat in the UK. Welcome, James.
Thanks very much for the welcome, and I felt really at home in the conference and talking to each other. It reminds me of something my plumber says. He's a religious man, and he says, being a plumber isn't a job, it's not a career, it's a calling. Everyone calls you. And so anyway, but in all seriousness, like I feel as though Phil Woolhouse before said, if he got $1 for every valve, he wouldn't be here. But I sense that he was passionate about what he did, and I sense that among people that are talking. So I'm just going to go through three questions. First of all, why hydrogen? Why is the British government interested in hydrogen? Second of all, if it all sort of makes sense financially or in the long term, would it be feasible to convert natural gas appliances to hydrogen? And so if that all lines up, would it be possible to convert the whole of the British infrastructure and houses to hydrogen appliances? So here we are. As I said before, we're just a systems and engineering technology consultancy, which is quite broad. I guess we do a broad range of things, anything from nuclear, wind, hydrogen, defence, rail, and obviously when the British government were looking to do this investigation in hydrogen, they came to Frazer-Nash. We'll add in a sly comment if they were looking to help with the problem of Brexit. I'm not sure whether we would take up that contract, but yeah. All right, so the first question, why hydrogen? So similar to Vikram's slide, this is, so the British government have got target zero by 2050, so that doesn't necessarily mean zero carbon emissions, but on average, zero carbon emissions into the environment. And so they looked at, all right, where are we using energy at the moment? Again, similar to Australia, transport, electricity is pretty constant, but heat fluctuates, obviously seasonal, and at different times was 3 times higher than electricity. So that's a significant area that they want to focus on. So then you look at the current infrastructure. It's a little bit complicated, but fundamentally any new buildings, I want to make sure are energy efficient, and low carbon heat. But I guess this bottom right-hand corner here is where this study was focused in. What do you do with the millions of houses already with installed natural gas appliances? Should we change them to electrification, hybrid setup, or go all out with full hydrogen? So kind of like, I think of this as like buying a car. You go out on the weekend, decide what you want to buy a car, and then you weigh up all the options. The British government is investing, I think, £27 million in looking at the different options. So they're having a red hot go. First thing to note is natural gas on the left is obviously the cheapest. But what is interesting is hydrogen, electrification. The different options are kind of like all pretty similar. So there's not one that stands out, wow, that'd be heaps cheaper. So hydrogen is still, in the running as an option. Just so I guess we're all on the same page. For me, it's helpful just to go back to basics, a bit of Chemistry 101, where why hydrogen is important. As we can see with natural gas, pretty much if anything you have a C on the left, carbon, you will have a C on the right. And with natural gas, you can see that produces CO2. With hydrogen, you have no C on the left, so then you have no C on the right. I guess the question that normally comes to my mind is, well, with people is, well, where does hydrogen come from? And right now, the biggest industrial production of hydrogen is from natural gas, in which case then the CO2 is produced there as opposed to in your house. However, as was discussed earlier, through electrolysis, you can reverse the hydrogen equation, therefore no CO2 is produced. And effectively, it's just a large battery, which makes the hydrogen equation more palatable. All right, so we'll just talk about are hydrogen appliances feasible? Again, I'm conscious I'm in a room with experts in the field of plumbing, whereas it's not necessarily my specific area of expertise, but just so that we're all on the same page, I'll talk with a standard domestic hob or a cooktop. So you have gas coming in, the natural gas, under pressure, through an injector or valve, whatever you want to call it, mixes with primary air, produces a mixture, then travels further up, and then mixes with the secondary air, is ignited, and then there's a thermocouple there to pick up if the flame goes out, which will turn off the valve. It's a pretty tried and tested system, safe, well regarded in the community. So what would happen? So Vikram spoke about a blended mixture. What would happen if we just went all out, 100% hydrogen? So the first thing to note is the flame is less visible. So there's safety implications regarding that, whether or not the users would be able to see the flame. There's also aesthetic implications for heaters, for example, where the gas flame is an aesthetic thing. How does that work? There's the proposal that in the same way that natural gas is odorless, but we add smelling substance to it, we could also do that with hydrogen so that it is visible. The flame speed is 7 times faster than natural gas. So in terms of safety devices catching, if the flame travels back down the source, the system would have to be retuned for that flame characteristic. And also going back to the chemical equation, you can see that molecularly hydrogen is smaller than natural gas. So it has more chances of leaking through gaps, like very small gaps that natural gas might not. Another item is the flammability range. So again, it's quite interesting for me to go back to the basics. You can see here that for every 1 molecule of natural gas, you require 2 molecules of oxygen, whereas on the hydrogen equation, you need 2 molecules of hydrogen to 1 molecule of oxygen. So you fundamentally need less oxygen with hydrogen. Whoops, sorry. So, and that we see that in experimental results, that the flammability range of hydrogen is 4 to 75%, which fundamentally means it'll burn at a lot richer mixture compared with natural gas of 4 to 17%. So that's good, I guess, but increases the chances of detonation, and there's a lower ignition energy required. So all of these primary air coming in and the spaces increase the chances of, I guess, an explosion that could happen if we were just to straight out change it to a hydrogen. So we could fix that by removing primary airflow, reduce internal spaces, ensure that a controlled ignition and a fast-acting flame device for the 7 times flame speed, and develop new seals to avoid leakage. But I mean, nothing stood out as hugely complicated in the same way that we had to develop the natural gas burners at some point. We would have to develop something for hydrogen, but you just couldn't swap it over one for one. Now just look at boilers. Again, conscious that a lot of people know more about it than me. First thing we'll note is a fan to mix air. Again, lots of air going in. A burner. The flame sensor will be an ionizing sensor or something like that in a boiler. The heat travels down so that the water obviously won't put out the flame, so the condensate comes out the bottom. Nothing too complicated. So again, we'd probably want to replace the pre-mix burner so there's not as much air going into the system. a new flame failure device. The ionizing sensor relies on the emission of carbon, whereas could use something like a UV sensor, which I think some appliances have, but we would have to, make sure that was correct. The heat exchanger for hydrogen needs to be developed, and obviously increasing the sump, because we're going to be producing more water. And so I guess they looked at how we could implement that. There's no real huge commercial involvement at this stage in terms of developing hydrogen appliances that we were aware of from the study, mainly because there's no real need for it. But if that was funded by government, how would we roll it out? We could adapt the existing natural gas appliances through taking out the burner on the hob. Now, I think that would be less palatable for the hot water or the boiler, because I guess that has a lot more in it that you would have to swap out. But for a cooktop, I think that might be more palatable. You could have new hydrogen appliances, so when it comes time to change over, you just take out the old unit, plug in a new one. I like the third option the best, starting to roll out hydrogen-ready appliances. So right now they will come ready for natural gas, but easily you could unscrew the cooktop or something and then screw in the new one later on. All right, so if that all lines up and we invest in the product, could we roll that out to the millions of houses in the UK? And my first thought for me was like, well, that'd be a huge task, but they've done it before. With the town gas, I'm sure different people here are aware of that. In the UK, they converted roughly 40 million appliances in the 70s. It took them about a 10-year period. And interestingly, if we compare that to now, from an appliance perspective, based on the data that we have, there's only about 44 million gas appliances. That's what the data is saying. The big difference, I guess, is 80% of homes now have gas central heating, which increases the complexity. But based on past experience, it is achievable. So if we look at the figures, how long would it take if you were to say a day to convert each boiler, half a day, or hot water unit, whatever you want to refer to it as, half a day for a fire cooktop, and based on the number of appliances that the UK government had, plus some survey, checking the pipework in the house, checking for leaks and making updates where appropriate. They estimate about 52 million person days, which is a lot of work. But if you were to just say, all right, could we do it? They have about 130,000 qualified gas-safe workforce at the moment. If they dedicate 10% of their working time, it'd take approximately 16 years. Remembering the target is for 2050, so it's a long-term project. Or likewise, if 100,000 dedicated 50% of their time, they could do it in 4 years. And again, based on the past experience in the 70s of 10 years it took them, it seems achievable. But what are the differences with the town gas conversion? Firstly, Vikram spoke about, I guess, the consumer's perspective. They want to know about the cost. Well, right now, hydrogen necessarily isn't cheaper like putting aside government subsidies. And as well, full hydrogen isn't necessarily safer. And the attitudes to health and safety have evolved over the time. Increase the complexity of appliances. The chances of 2 people in this room potentially having the same oven or cooktop or boiler is probably limited, but whereas back in the 70s, that was potentially increased and it was just in the UK or Europe region, whereas now it's more global and increases that complexity. And warranties as well. So if we did the changeover where we came out, took out the natural gas and put in the hydrogen, who would be responsible for the warranty? And as well, after all of that, if the customer, just says, all right, no, I'm not interested, now they have the option of getting an electrical, cooktop or a heat pump, and then, just go right around the problem. So in conclusion, The key issues seem to be demonstrating safety to the consumer and getting consumer acceptance, and developing the systems to exchange the hydrogen-ready appliances, or whether or not to convert it like at the time of conversion. I personally like the idea of rolling it out in advance, taking the pressure off the time of the point of changeover. And based on the data that they've looked at, they estimate anywhere between 4 to 16 years, depending on the size of the task force. If you'd like to look at a bit more of a detailed report, you can search for BIS Hydrogen Appliances or BIS Hydrogen Logistics. They're a detailed summary of the report that was presented to the British government. Thanks for your time.